Okay, so today we are going to look at a few more examples with linear and angular speed. And we're going to kind of compare everything that we find. All right, so just as a reminder, these are the formulas we have for both. All right, so linear speed is, remember, S means our arc length over time, right? So how fast we travel around the circle, okay? But in reality, we're taking that circular motion and we're kind of laying it out flat, okay? And then angular speed is the rotations we do over time, okay? So this is truly your circular motion when we talk about angular speed. Okay, and then we also had, if we find the angular speed first, we can find the linear speed by multiplying the angular speed by the radius. Okay, and we get this equation by substituting in angle over angle time radius for arc length, right? And then we just manipulate our functions. Right, so they'll be up there for our reference we can go back to if we need. So the example we're going to look at today, the blades of a wind turbine. All right, so right, those giant windmills that you might see. All right, so the wind turbine has blades that are 116 feet long. All right, so they're pretty big. The propeller rotates at 15 RPM. So I'll address that in a second. So we're going to do three things. We're going to find the angular speed. Now, usually they tell you the units because our time is what matters. All right, so angular speed is always going to be radians per unit of time. So radians per second, radians per minute, radians per hour. So there we just got to be careful how they tell us it's rotating. Okay, so here, RPM. Okay, it means rotations per minute. So in 1 minute, if this top blade starts up here at the top, right, in 1 minute, it's going to go around 15 times. Then we're going to find the linear speed of the tips of the blades. So if somebody was sitting at the top of the blade and going around, how fast would they be traveling? And then we're also going to find the linear speed of the midpoint of the blades. Okay, so halfway there, and we're going to compare everything. All right, so for part A, we want to find the angular speed. So I don't know if I mentioned this. This is just kind of a side thing. This isn't just a W. Okay, it is a lowercase Greek letter called omega. All right, so that's why it's kind of, I don't just draw the W like that. Right, it's kind of curvy. All right, so that's in most sciences. Right, and if you're in physics or anything like that, anytime you talk about angular speed, we use the omega. So we're going to be calculating the omega, and again, that's just going to be the rotations over time. So we have to be careful how we figure out our theta. Okay, theta is our total radians rotated. Right, so we're going to dissect this 15 RPM. So 15 RPM actually tells us two things. Okay, it's going to tell us both our theta and our time. Right, time is the simple one. Time is just going to be 1 minute. I want to find the angular speed in minutes, right, radians per minute. And this is 15 rotations per minute. All right, so that's simple. Our t is 1. We're dividing by 1. Not too difficult there. Our theta, though, we got to be careful. So I'm making 15 full rotations. But if we look at the units, my angular speed is in radians per minute. Here, my theta, I don't have it in radians right now. I just have 15 rotations. Well, what do we know about one full rotation? If I make one full rotation, that is 2 pi radians. All right, so anytime we make a full rotation, you automatically have 2 pi radians. So since we're making 15 rotations, we're going to say we covered 30 pi radians. Okay, and all we do there is we multiply the 15 times 2 pi. All right, and like I said before, we're going to keep pi there. We're not going to multiply by pi. If at all we're going to do that, we're going to save that for the end. Okay, that's the last thing we do. So my angular speed is going to be 30 pi radians over 1 minute. So it's going to be 30 pi radians per minute. And here is where we would like to find the actual numerical value. So I'm going to find 30 pi. So we're covering our angular speed is about 94.2 radians per minute. But since we are talking about radians and we are talking about angular speed, we can leave it in terms of pi. All right, so this would be an acceptable answer. All right, I wouldn't mark you wrong for this, but this is a little neater. Right, we don't have to round anything there. Okay, any questions about finding that? So there, the only thing I'd really worry about, that might pose you problems is the theta. All right, so just be careful. All right, so now we want to find the linear speed. All right, so again, if there's a person sitting at the top of that blade and they're spinning, right, they would feel like they're moving. If they felt like they're moving in a straight line, okay, we could calculate the linear speed. So I'm going to show you both ways. I'm going to show you this way first, and then I'm going to show you with the quicker way. So first, if we calculate our arc length, okay, well, that's going to be kind of like what we did here. So the arc length is the radians we covered times r, right, our radius. So the radians we covered, we have up here as 30 pi. We're going to multiply that by our radius, right? And our radius is the length of the blade, which is 116 feet. So we can multiply those two together. And now since we're talking about arc length, we're back to regular distance. So I'm going to do the 30 pi as a decimal times 116. So the arc length that I'm covering is 10,932 feet. I'll say 0.74. So rotating 15 times with a radius of 116 feet, all right, if you mapped out how many, the actual distance you covered going around 15 times, right? It would be 10,900 feet. So again, right, the other part that I need is time. Well, this all happens in 1 minute, right? So our linear speed is going to be s over t. So it's going to be 10,900. 10,932.7 feet per minute. Okay. And again, you can kind of see right here, if I multiply my linear speed times the radius, right? That's the other way of finding out our linear speed. I'm sorry, our angular speed times radius to find the linear speed. Well, in this case, it's literally just the same thing that we did here. Right? So we get the same thing there. So for our last one, I'm going to do it the quick way, but I want you to think about this for a second before I actually do it. Okay. Now we are finding the speed of the midpoint of the blades, right? So in between, right, where it rotates and the end, okay, if I am essentially taking half of my radius, you don't have to say it, but you can think it. What do you think will happen to the linear speed, right? If I'm halving my radius, if I'm taking, a less radius, what will happen to the linear speed? Well, my angular speed is going to be the same, right? My angular speed, I'm still traveling 30 pi radians per minute. Okay, that's not changing. But now, instead of multiplying by 116, I'm going to be multiplying by, nope, not 53, 58. All right, so when I multiply those two, all right, we get half of that original linear speed. Right? So our radius is directly proportional to our linear speed. Right? If I doubled the size of the blade, if I said we had 200-foot blades now, okay, our linear speed would double from that original. Right? So the linear speed, like I think I mentioned this last week, the linear speed is directly dependent on the radius. Right? The larger the radius, the faster the linear speed. Right? And I showed you the circles, right? Because they're traveling in a rotation in the same distance, but technically, if I have a larger radius, I have to travel further, but I'm covering it in the same time, right? If this is a solid bar that goes here, and I rotate it around, the tip of the bar has to travel faster than the middle of the bar in order to make one full rotation at the same time, right? So the linear speed would be faster than with a larger radius. All right, let's take a look at one more example. All right. So now we're taking a look at a blade saw. Right. So that's you know, you guys don't have shop class anymore. That's one of those saws that's part of the table, right? And it spins around really fast. And you push the wood and it cuts it however you want to cut it. So the blade saw has a diameter of 8 inches and it rotates at 2,400 RPM. Right, so those things got to spin really fast in order to cut whatever you're trying to cut. Right, so in 1 minute, the tip of the blade rotates around the axis 2,400 times. Right, pretty quick. So this would be similar to, say, a car example, right? So the gears inside of your car, right? Again, if you look at the dashboard, you'll see the RPM meter, right? So that's in thousands, right? So if you're up at 3, that means the gears, the fan inside of your car engine are rotating at 3,000 rotations per minute, right? So that's pretty fast. All right, so we're going to find the angular speed. So again, they didn't really specify how long it's rotating, right? So since they give us RPM, your time is going to be 1 minute. The angle that we cover, right? Again, one rotation is 2 pi radians. Well, we're covering that 2,400 times, right? So the angle that we cover is going to be pretty large. 1 second. Oh, no, okay. Right, so we're going to multiply 2 pi times 2,400. Right, and that's going to be over 1. So our circle, our blade, is rotating at a speed of 4,800 pi radians per minute. Okay, and as long as we're in angular speed, you can leave the pi there. It's a little easier. You don't have to round. You're not dealing with any decimals. Okay, the linear speed. Just be careful with the information we're given. Right, they tell us that the diameter is 8 inches. So if the diameter is 8 inches, then our radius is 4 inches. All right, so our linear velocity, again, we can find by multiplying the angular velocity by the radius. So we have 4,800 pi times 4. All right. Yeah, so again, they didn't specify what units that they want the answer in. So this is inches, right? So our answer is going to be inches per minute. And when we multiply all that together, okay, we get 60,318, and we'll say 0.6. Inches per minute. Right. Any questions?
It's not on this, but we don't take midterms, right?
I'll just give me a second. I'll answer that in a second. Any other questions about this?